So today we're going to start chapter 12. Chapter 12 is what is going to be your last test, and chapter 12 is on probability. So today we're going to talk about sample spaces and basic probability, both theoretical and experimental. So first we need to go through a few definitions. So a probability experiment is just an action or a trial that has varying results. So for example, you could do a probability experiment where you flip a coin 10 times and then you write down what you get, how many times you get heads, how many times you get tails. The outcome would be the possible result of an experiment. So when I flip a coin, my outcomes are either a head or a tail. If I roll a dice or a die or a number cube, there would be 6 possible outcomes. The numbers 1, 2, 3, 4, 5, and 6. An event is an outcome or a collection of outcomes. Like for example, when I roll my die, if I get a 2, 4, or 6, that would be rolling an even number. That would be an event. And then the last one is the sample space, and that would be the set of all possible outcomes. So for example, my sample space, when I flip a coin, that would be heads and tails. When I roll a die, my sample space would be 1, 2, 3, 4, 5, and 6. Let's try some examples. So you're going to flip a coin twice. It wants us to figure out how many possible outcomes are in the sample space, and it also wants us to list the possible outcomes. Now, probably in middle school, they made you do tree diagrams. If you did a tree diagram in middle school, a tree diagram for example 1 would look something like this. So when you flip a coin, you know your options. You're either going to get a head, and we'll call that H, or you could get a tail. Then the other thing that they want us to do in this problem is flip the coin a second time. So when I flip it a second time, I could still get the same outcomes, a head and a tail. So if you had to fill in a tree diagram, so this would be the first one, this would be the second flip. So then if you follow this up, a head to a head, so I could either get, when I flip my coin, first flip is a head, second flip is a head. Or first flip a head, second flip would be the tail. Here, I could flip and get a tail first and then a head, or I could flip it 2 times and get 2 tails. This is all of my outcomes. Notice there are 4 outcomes. One way that you can do that is you could multiply the number of times you do it times the possible outcomes. So 2, and then there's 2 outcomes. It's head or tail. And then that's how I can double check my list here, that there should be 4 outcomes when I flip a coin twice. Now it's asking us, we're going to flip a coin and roll a number cube. When you see the description of a number cube, they're talking about a regular die. So, and that would have 6 different numbers on it. So it wants us to find the possible outcomes and how many are in that sample space and to list them. So again, I could do a tree. So if I put the coin first, remember my options are head or tail. And then for the die, or the number cube, they called it a number cube, same thing. I would get a head with a 1, or I could roll and get a head with a 2, a head and a 3, head and roll a 4, head and roll a 5, and flip the coin and get a head with a 6. Then I'm going to do the same thing with the tail. When I flip the coin, and let's say instead my coin landed on tail, and then I roll the dice, I could get a tail with a 1, a tail with a 2, on the dice, a tail with a 3 on the dice, a tail with a 4 on the dice, with a 5, and with a 6. These are all of my possible outcomes. There are 6 when I roll a head, and then 6 for the tail. So a total of 12 outcomes. Again, you could use what they told us to do is on the coin there are 2 outcomes. On the die there are 6. 2 times 6 is 12. So I should be able to calculate or count 12 different outcomes here. Now sometimes when you're doing probability, you're going to need to figure out all of the outcomes before you can answer the question. Now let's talk about simple probability here and whether it's likely or unlikely. So that's what's on the next slide. So the probability of an event is really the chance or the likelihood that an event will occur. Probability is going to be a number between 0 and 1. However, you can also represent it as a fraction, a decimal, or a percent. The notation or the way that you would write or see a question is they're going to put a capital P, and then in the parentheses will be the event. Like, for example, if it were a coin, and they say, what is the probability of the coin landing on a head? That's how you would write that. So whatever kind of description you want to put for your event, you could put that in the parentheses. Now, when the probability is 0 or 0%, you know that this is not going to happen. It's impossible. If it's 1 or 100%, then that's certain. Then you can slowly go into the middle. When you get smack in the middle here, and it's at 0.5 or 0.50 or 50% or 1/2, then you know that it's equally likely. It could, 50%, or not happen. Then the closer you get to 0, the 1/4, the 0.25 or 25%, the more it approaches 0, the less likely it's going to happen. Then if you go in the other direction, the 0.75, 3/4 or 75%, then it becomes more likely. So the closer it is to 1, the more likely it will happen. So again, probability can be represented as either a percent, decimal, or fraction. So let's see what theoretical probability is. So theoretical probability can be found when all the outcomes are equally likely to occur. So theoretical probability is defined as the number of favorable outcomes, what you're trying to get, over the total number of outcomes. So for example, with the coin, let's say we're flipping our coin and we want to find out what is the probability of the coin landing on heads. We know that the number of favorable outcomes on my coin, there is only 1 head over the 2 outcomes, which are head and tails. If I were rolling a number cube or a die, and I wanted to know what is the probability of rolling the number 2, I know that there is only 1 number 2 on the die out of the 6 different outcomes. Same thing with the coin as well. The dice. Let's say I wanted to know the probability of it landing on an even number. So I know there's 6 different numbers, and I know of those 6, 2, 4, and 6 are even. So 3/6, and you would always simplify it, and that probability would be 1/2. Now, theoretical probability is what you think should happen. And again, it says that they're equally likely to occur. However, in the case of the coin, let's say you flip the coin 10 times. Theoretically, 5 of those 10 flips should be heads, and 5 should be tails. However, what you think should happen doesn't always happen. Sometimes maybe you flip that coin 10 times and a head will appear every single time. That is going to be covered also later in the slides, and that's experimental probability, where you actually do the flipping of the coin and you write down how many times it occurs. So we will see both theoretical and experimental. Theoretical, again, is what you think should happen, whereas experimental is when we're actually going to do an experiment and write down the results. Let's do some examples of theoretical. So here, again, we're tossing a coin and rolling a number cube. It wants us to find the probability that the coin is going to land on heads and the number cube is going to be a 5. So here is where I need to write out my sample space. And I already did it for this, but I'll rewrite the possible options again just so we can see it. So rolling the number cube, remember it's either a head or a tail, but then we have to also incorporate the number cube. So we know we can either get a head and a 1, head and a 2, 3, 4, 5, and 6. And then the same outcomes here when I flip and get a tail. And you can count them, and there is a total of 12 different outcomes. So remember, the denominator is the total number of outcomes. The numerator is what you were trying to get, and we were trying to get a head and a 5. There is only one time in this list of outcomes that will occur, so this answer is 1/12. Now also remember, you can also represent this as a decimal. So you would just divide 1 by 12, and as a decimal, it's actually 0.083 repeating, and as a percent, it would be 8 1/3%. Most of the time, the probability is they're gonna ask you to write it as a ratio or as a fraction. Then for part B, they've given us the data in a table form. They want us to find the probability that a t-shirt that is chosen has a gold emblem on it. So whenever your data or information is given to you in table form, we may have to go back and add some of the columns to get our totals. So I know there is a green shirt with a gold emblem and a red shirt with a gold emblem. And that total with gold emblems is going to be 10 plus 6, and a total of 16 shirts that have a gold emblem. Then there is a silver emblem as well, and I'll add 8 plus 6, and that gives me 14. The total number of t-shirts we're talking about here is going to be 16 plus 14, and a total of 30 t-shirts. Remember, for probability, we need to know the total. So this probability is going to be 30, and then if I go and figure out and grab the number for the gold emblems, that's the 16. So I'll put 16 over 30. Always reduce your fraction, and the probability of pulling a t-shirt that has a gold emblem, they didn't care about the color of the t-shirt, is 8/15. And again, remember, you can also represent this as a decimal, which actually turns into 0.53 repeating. If I move my decimal point 2 times to the right, I could also make it a percent, and this would be 53 1/3%. So again, remember, the probability can be represented as a fraction, decimal, or percent. Again, the most common way that you'll probably see this on an SAT is in fraction form, but be aware either one will also result. Next, we're going to talk about the probability of the complement of an event. So when they talk about the complement, think about complementary angles, If you think about two angles, when they're complements, they have to add to 90. If you know one, remember you just had to subtract it from 90 to get the other one. This is sort of similar. Remember that a certain thing happening is 100% or 1. So if an event of it happening, say, is 50%, then not happening would be 50%. You would have to add them and it should equal 100%, or if they were decimals, you would add them and it needs to equal 1. So this is read as a bar, if you ever had to say how to read that. But that is the symbol for complement, and to find it, you just take the probability they give you of the event and subtract it from 1. So I would subtract 0.45, and the complement of event A is 0.55. Sort of think of it like rain. Like, let's say the weatherman says, there's a probability that the chance of rain today is 40%. The complement of that, of it not raining, would be 60%. So you can just think of it like that. Next, we're going to talk about geometric probability. And this is going to take us back to chapter 11. We're going to need to find areas when you're given a geometric question. Now, prior to this, in our old textbooks, this was actually its own lesson, where we did a whole bunch of homework problems just on geometric probability. So here is one example, and there's probably maybe one or two in the homework as well. Whenever you're doing a geometric probability, that can be found by calculating a ratio of either two lengths or two areas or volumes. In this case, it's a dartboard, and it says you throw a dart at the board shown. It says your dart is equally likely to hit any point inside the square board. So it can hit the red or the pink, the yellow, the green, or the blue. It's equally likely to hit any of those spots. And it wants to say, are you more likely to get 10 points or 0 points? So they're basically asking, is it more likely that you would hit the pink area or the blue? So what we need to do is calculate the area for each. So let's do the pink one first. So we're going to find the probability of hitting the 10-point area. And what we need to do here is, again, remember we're going to do the whole entire area is the denominator. So this will be the area of the entire board. That's going to be the denominator, and it's a square, and it's going to be 18 by 18. Then the numerator is going to be the pink circle. So what we need to do is find the area of that smallest circle, or the pink circle, and then that's going to be our probability. So my radius of that pink circle is 3. Notice the 3 and the arrows it's pointing to. We learned the formula for area of a circle in chapter 11, and we know that that is pi times radius squared, so pi times 3 squared. The whole board is a square, so it's 18 times 18, or 18 squared. So then this is going to become 9 pi over 324. I could reduce this and make it pi over 36, but I'm going to go ahead and just divide it. And my probability here is 0.0873. So in fraction form, you could leave it as pi over 36. As a decimal, this is going to be easier to compare. Now let's do the probability of hitting the blue section. So the probability of 0 point section, again, we're going to do the area of the entire board again as the denominator. But for the blue area, what I need to do is, it's going to be the area outside of the largest circle, which is that blue part. And the way that we're going to do that is we're going to take the square and subtract out that largest circle. So the square, remember we just did it, it's 324, 18 times 18. And then I'm going to subtract the area of the large square, which is going to be pi times 9 squared. And then it's over the entire board, which was 324. Pi times 9 squared, which is 81. So it'll become 324 minus 81 pi over 324. And then here, when I divide this, I get 0.215. Notice this number is larger. So then this will actually become this, you're more likely to get 0 points, because it's the larger probability. This one's larger. Next, we'll take a look at the experimental probability. Everybody good here? Next is experimental probability, and again, this is based on repeated trials of an experiment. So for example, flipping a coin 10 times, rolling a dice 20 times, and writing down what you got each time you flipped or each time you rolled, or whatever experiment you want to do. So again, the number of trials is the number of times the experiment is performed. And then success is, in each trial, your favorable outcome. So for example, flipping the coin, let's say you're trying to get heads every time you count that you get a head, that would be the number of successes over the number of times, say, you flip the coin. So this would be something that's already been done, and they probably have written down the results for you to calculate the probability. So that's what we're going to see in the next example. So we have a spinner. All right, so they've spun this spinner with the blue, the yellow, the green, and the red sections, and they did it 20 times. And then they wrote down the results of those 20 spins in the table. Now, keep in mind, when you're doing this experiment, there are different factors that can affect the results. Let's say this spinner was sitting on a table that was slanted, and maybe it was, leaning more where it was more likely to land on the green the way that the spinner was sitting on the table. So sometimes there's outside things that can affect a spinner, because theoretically it should land on the blue, the yellow, the green, and the red the same number of times. But again, when you actually do something, that's not always the case. So what they want us to do is figure out, based on these experiment results, which color gives us the same as the theoretical probability. So let's go through and check it. So for the experimental probability, for each color, let's go ahead and do it. So we would take the number of times it landed on red, that was the favorable, over the total number of spins, which was 20. Simplify, and that's 1/4. Then we take the green, and we'll do the same thing. 9 over 20, that one can't be simplified. Then the blue, 3 over 20. And then lastly, the yellow, I'll write that in black because the yellow writing doesn't come out very well. So that's the yellow. Now, it wants me to figure out which one of these probabilities is the same as the theoretical. Now, for the theoretical, we don't take into consideration the spins. We just count how many sections there are, and there's 4 sections. And let's say it doesn't really matter, because the theoretical probability of red is 1/4, of green it's 1/4, of blue 1/4, and of yellow 1/4. The only one that is the same as the experimental is the red. So again, when it's experimental, you need to take into consideration the total number of times they did something, whereas theoretical, you would just take, the number of different colors you had over each one. So red, blue, green, and yellow, theoretically, 25% of the time it should land on one of those. But as you saw with this results, that's not what really happened. So the only one that was going to be the same is red.